All right, so welcome to the third problem that we're going to look at. So we have a cantilever beam. This time we have a distributed load of 15 kilonewtons per meter, and it's increasing. It's increasing as we're going. So it's like a triangular load. First, we need to find our reactions, and then second, we can find our shear and moment functions. All right, so let's draw our reactions. So we're going to have an AY reaction, we'll have an AX reaction, and we'll have a moment, which will be MA reaction. So first thing that we need to do, solve our reactions. We need to write our equilibrium equations. So we can go sum of forces in the X direction are going to be equal to 0. So any forces going forwards or backwards, we'll go backwards will be negative, forwards positive. So we don't have any forces going forwards or backwards on the beam. We just have our reaction. So we can just write AX is equal to 0. Then we have sum of forces in the Y direction equal to 0. Any forces up or down, up will go positive, down we can say is negative. We have our positive reaction going up, so we can write positive AY, and we have our negative load going down on the beam. So the total force of this load, this triangular load, will be half the base times the height. Okay, so the base is 3 meters and the height is 15 kilonewton meters. So the force is acting down, so we can write negative half the base, which is 1/2 times 3, times the height, which is 15 kilonewtons per meter. This will be equal to 0. So if we solve for AY, we'll end up with AY is equal to 22.5 kilonewtons. And finally, our third equilibrium equation, sum of moments about point A. So let's say this is point A, and this will be equal to 0. So any forces acting in the anti-clockwise direction, we'll say is positive. Any forces acting in the clockwise direction, we'll say is negative. So we have our MA in the positive direction going in this direction. We can write positive MA. So this triangular load has a force acting in this direction. So this will be the clockwise direction. And we know that this total force is 22.5 kilonewtons. So we need to know this distance up to here. So on a triangle, the centroid of the triangle, so the force will act here, and this distance is 1/3. So if you see a triangular load, it's going to act 1/3 the distance. But we're interested in this side, so 2/3. And because this triangle is 3 meters, this will just be 2 meters. Our distance is this 3 meters plus 2 meters. 2 meters here. So force is acting in the clockwise direction, so minus 22.5 kilonewtons times 5 meters. That will be equal to 0. So a moment at point A will be equal to 112.5 kilonewton meters. All right, so now we've solved our reactions, and now we can go on to solving our shear and moment functions. So let's redraw our beam with our reactions. All right, so we've drawn our beam with our reactions, and we can draw our shear and moment, bending moment diagrams. So we'll have our shear force diagram, and we'll have our bending moment diagram. If we look at our beam, we know that we'll have a positive 22.5 kilonewtons here. There are no forces acting until we reach our 3 meter point. And then we have a changing distributed load. So that means our shear force is going to look something like this. And then we'll end up with 0 here. So between our 3 meter point and our 6 meter point, we don't know any of these values. We need to come up with a moment function to find any point between here. So we need to develop our shear function to find any point along this curve. And if we look at our bending moment, we'll have a negative 112.5. So we'll have a curved line up until our 6 meter point, and then this will be 0 to the end. So we don't know any of these values. We don't know any of these values. We need our moment function. So let's find our shear and moment function. So if we redraw our beam, so what we'll do is we can make a cut section here, and we can make a cut section here. Let's start with our first cut section. So our beam is going to be here. It's going to be cut at this point. We have our reactions, we have a moment, and then we have our shear. We're going to draw it in the negative direction, call it V1, and we have a moment, and we'll have it in the positive direction. We'll call it M1. And our distance is going to be X1. So let's write our shear as a function of X1. All right, so our V1 is acting in the negative direction. So we can write negative V1. And our reaction is in the positive. So we can write plus 22 22.5, and this will be equal to 0. V1 is equal to 22.5 kilonewtons. And then we can write our moment function. So moment as a function of x1. So we have a positive moment going in that anti-clockwise direction. So we can write positive m1. And we have a negative moment going in this direction, which is a 22.5. So we can write negative 22.5 kilonewtons times the distance of x1. Distance of x1 meters. And then finally we have our 112.5 kilonewton meters in the positive. So we can write 112.5 kilonewton meters equal to 0. We don't have any other forces, so we can just write m1 is equal to 22.5 x1 kilonewton meters minus 112.5 kilonewton meters. So now we found our moment function and our shear function for any point up to our 3 meter point. Yeah, any point up to here. We just found that. We can plug in 1 meter into this x and we can find our bending moment at 1 meter or any point we choose. All right, so let's find our second section. So we need to draw the beam again. We have our distributed load now. We'll say this distance is x2. We have our shear. We have our shear, V, we'll call it V2. And we have our moment. We can call this M2. All right, so let's find our shear. So our shear is a function of x2. All right, so we have our negative V2 acting down. So we can just write negative V2. We have our positive AY plus 22.5 kilonewtons. And then we have this triangular load. All right, so this is actually a really interesting problem to solve. We don't know this value here, this value here. We don't know what it is. We're developing a function of x2, and we haven't defined what x2 is. We haven't defined it, so we don't know what this value is. So x2 can be anything, so between this point and up until 3 meters, right? And this point we can say is 0. So we're trying to develop an equation where we can just plug in a number and it will give us this force. But we haven't defined this. So what we can do is we can use similar triangles to develop a formula for this. So this is just a little sidetrack. So let's redraw our triangle, and we know that our full triangle this is 15 kilonewtons per meter. Here we have 0, and we're finding a point, like an arbitrary point, along this x2 distance. And we know this up to this point is 3 meters, right? So up to this point, we know that this is our triangle, right? This is our triangle. We also know the area of a triangle is half the base multiplied by the height, right? So we also know this. These are two ideas that we need to have. So we know our B is x2, but we don't know what our height is. If we use similar triangles, we can find this point. So we can write 0 minus 15 divided by 0 minus 3, all right? And that will be equal to 0 minus, let's say this point is h, minus h, divided by 0 minus, and we have our x2 point here. We have an x2 point, x2. And if we solve this, we'll find this to be 5x2 is equal to h. All right, so we've found our ratio that we need. So we've written our h term in terms of x. And now we know what our h value is. So we can plug in 5x into here. All right, so we'll have a negative 1 over 2 multiplied by x2 multiplied by 5x2. And this will be equal to 0. So if we get rid of all of this, our V2 will be equal to 22.5 kilonewtons minus 2.5 x2 squared. Now we have our shear function, and we need to do a similar thing with our moment function. Okay, so if we write our moment as a function of x2, we have our positive moment acting in the anti-clockwise direction. So we can just write positive m2. We also have our 112.5 kilonewtons. So we can write positive 112.5 kilonewton meters. We have a negative 22.5 kilonewtons multiplied by this distance here. And this distance is 3 plus x2 meters. Finally, we have our moment from our load, right? It'll be acting in this direction. So it will be a positive. It'll be a positive moment. It's acting in the anti-clockwise direction. And we know our force. This is in kilonewtons, right? This is in kilonewtons. And we know what this triangle will be as a function of x2. As a function of x2, we know this force. So this force, we can write 2.5 x squared. And the distance, if we go back to our beam, the distance will be here to this point. And this distance is a third. So it's going to be a third of the triangle. And the length of our triangle is x2. So it'll be x2 over 3. And that will give us our moment. That'll give us our moment. So we can go multiplied by x2 over 3. Just to clarify, this is our kilonewtons. And then this one, all of this is kilonewton meters. All right, so if we solve for M2, we'll find this is our moment function, and we have our shear function for x2. If we go back to our beam, what we just found was any numbers between this point, these 2 points. So this is our x2, and this is our x1. We want to find the point at 5 meters along the beam. Maybe it'll be 5 meters will be roughly here. We can plug in 2 meters, and we can solve our moment and shear function at this point. Okay, so if we write our shear as a function of 2 meters, so we can write 22.5 kilonewtons minus 2.5 times 2 to the power of 2. And this will be 12.5 kilonewtons. And if we find for our m as a function of 2 meters, we'll have negative 2.5 times 2 to the power of 3. 3 plus 22.5 times 2 minus 45. And this will be equal to negative 6.67 kilonewton meters. So what that means, at this point in our beam, this point, which is 5 meters across, we found it to be 12.5 kilonewtons. This is our shear value here. And our moment, we found it here, which will be negative 6.67 kilonewton meters.